Welcome to solverfy.
6.21, excuse me. So we want to determine the magnitude and direction of the effective acceleration due to gravity at a latitude of 45 degrees north on the Earth, which is a rotating, in this case we assume it's a sphere. It's not quite spherical, but... So to understand what this is even asking us, suppose here we are, like here's the equator, here's the North Pole. Here we are at 45 degrees north of the equator. The same, applies to 45 degrees south, I guess, but for the sake of illustration, let's say it's 45 degrees north. So now there's this point is going to be undergoing a uniform circular motion around a circle that sort of cuts through the Earth. The radius of this uniform circular motion is going to be the radius of the Earth times cosine of theta. I want to move that because I need to draw more things up there. So we're going to have the force due to Earth's gravity acting towards the center of the Earth. And then we're going to have a normal force which is going to be equal to negative the mass of our object times this effective acceleration of gravity. And this is not perpendicular to the Earth's surface, because these have to add up together to a net force that provides the centripetal force in this uniform circular motion. And we're going to use coordinates that have a y that's parallel to the line from the center of the Earth, or is perpendicular to the surface of the Earth at this point, and x that's tangential to it. So F net is equal to Fg plus Fn. And the magnitude of the net force, because this has to be a centripetal force, is going to be the mass times the centripetal acceleration. So we have negative gm times the mass of the Earth over the radius of the Earth squared in the j hat direction, plus F sub n, what we're looking to find, is going to be equal to the two components of of the centripetal force, so mv squared over r, times the sine of theta I hat plus the cosine of theta j hat. Negative cosine theta j hat. Because the y component is going to be negative. And so then just doing a little bit of algebra here, we get that f sub n is equal to mv squared over r sine of theta I hat plus g MEM over the radius of the Earth squared minus the centripetal force, v squared over r, cosine theta. This is the j hat component. So the speed of the uniform circular motion is 2 pi r, which is our re cosine theta, divided by the length of a day. So we get m times 4 pi squared re cosine theta divided by the rotational period of 1 day times the sine of theta I hat plus g times the product of the masses divided by the radius of the Earth squared minus our same 4 pi pi squared r e cosine theta divided by t squared I'm sorry, this has a t squared as well. And so we can put in some numbers for these things. So this is equal to m times 1.687 times 10 to the negative 2 meters per second squared in our I hat direction, which recall is parallel to the surface of the Earth at this point. Plus 9.783 meters per second squared j hat. This is the part that's vertical. So here is our normal force vector, which recall we said was equal to the mass of the object times our effective gravitational field, the minus sign there. So if we call the angle between f sub n and a perpendicular line along the y-axis phi, then that's the arctangent of the x component to the y component of the normal force, which is 0.0988 degrees. So it's not very far from being vertical. So it's this this angle north of the upwards direction is the normal force, but since the opposite of this divided by the mass is the effective gravity field, so our direction is about 1/10 of a degree south of north, or not south of north. That doesn't make any sense. South of being radially inward. And then taking the magnitude of this vector, because we took the mass out already. So we just take the square root of the sum of the squares of these two numbers here, and we find that the magnitude of the effective gravity is 9.78 meters per second squared.